Today we're going to hear from Lara Wagner, a geophysicist in our Earth and Planets Laboratory who uses seismology to understand the formation and evolution of the lithosphere, which is the outer rigid part of the Earth. Our planet is differentiated into layers, a core, a mantle, and a crust. And although we can't directly access the interior, Earth's interior, we can't see it, to observe geochemical processes, to observe motions and things going on in the depths firsthand, Lara is able to glean information about mantle dynamics by studying how seismic waves travel through the Earth. She sometimes compares her work to pointing a telescope down into the Earth's depths to understand what's occurring deep beneath the planet's surface. Using the seismic instruments that she is here today to tell us about, Lara is able to investigate subsurface structures that tell her about the processes that have shaped the continents. She also studies the interactions occurring between boundaries of modern tectonic plates, which can reveal details about the properties of the Earth's crust, including its composition, and the ever-important forces that cause the buildup of stress that can result ultimately in earthquakes. It's certainly possible that her research may have important implications for improving hazard assessments and natural resource development. Before joining Carnegie as a staff scientist in 2014, Lara was an associate professor in the Department of Geological Sciences at the University of North Carolina, Chapel Hill. However, her current position at Carnegie was a homecoming for her, as she had been at Carnegie as a postdoc between 2005 and 2007. Lara received her BA in History and Sociology at Columbia University, and then went on to do her PhD in Seismic Studies at the University of Arizona. She received the American Geophysical Union's Outstanding Student Paper Award in 2004, the Walter Wheeler Faculty Teaching Award in 2012, and was named an Incorporated Research Institutions of Seismology Society of America Distinguished Lecturer in 2013. All of these awards should tell you that she's an excellent communicator, which means, like myself, we're all in for an enjoyable and educational experience here today. So please join me in welcoming Dr. Lara Wagner.
All right, here we go. So let me see if I can make this technology work for me. Okay, can everybody see me? All right, great. I'm so happy to be here with you today. This is going to be a lot of fun. I love talking about my fieldwork. It's only part of the research that I do. This is the part where I collect the data that I then spend some quality time analyzing in the lab afterwards. But it's an important part. So I hope you'll join me for this, this journey through some of my adventures. And then I'm happy to take questions either about the fieldwork or about the analyses that we do later. Okay, so I wanted to start off with a bit of background on what exactly it is that a seismologist does. I'm a seismologist. So what is it that we do? I think there's some misconception sort of from popular culture on what it is that my day-to-day job actually looks like. Seismology is, of course, fundamentally the study of earthquakes. Seismos in Greek is earthquakes, and logia, study of. In fact, one of the early seismologists is Aristotle. His idea of earthquakes is that it was hot gases or gases erupting out of the earth that were causing the ground to move. We've picked up a few things since then. But yes, it is true that fundamentally, seismology is the study of anything that shakes the earth. That certainly includes earthquakes. Studying not only earthquakes that you feel and do damage and that have hazard implications, but also earthquakes that are much smaller or in places where people are less affected. But in addition to that, we also study things like nuclear explosions. Most of the verification treaties rely heavily on seismology to be able to detect and locate nuclear explosions. We can look at things like mine collapses, causes of mine collapses. Was it due to an earthquake or was it due to an implosion? We can look at source effects. Increasingly, seismology is used for things like intrusion detection systems, that kind of thing. They're very sensitive instruments and they will pick up pretty much anything walking by. So this is one of my favorite stories of studying things that shake the ground. And this comes from a deployment that my colleagues did in the country of Cameroon. So this was 40 broadband stations across the entire nation. And they kept having these seismic arrivals. So this is each of the stations, and this is the seismogram. I apologize for the blurriness here. But you can see that they all have this arrival coming in at exactly the same time across the entire country. And that would suggest that this impulse here is traveling at infinite speed, which seismic waves don't. And it was actually one of their students that put this together, that every time they had one of these pulses, it corresponded to a soccer goal scored by Cameroon in the 2006 Africa Cup of Nations. And so in this particular instance here, this was an overtime goal scored by Cameroon. They were down 1-0 to Ivory Coast, and they managed to tie it up. And there was apparently the entire country celebrating at once, impulsively, diligently recorded by all of the seismometers. Okay, so in addition to studying things that shake the ground, we also study the ground that's shaken. And so, as Eric mentioned, we study the interior of the Earth using seismic waves. And as he also mentioned, the Earth is a very layered structure. We have a solid inner core, a liquid outer core that gives us a magnetic field that allows us to have life as we know it, a solid but deformable mantle. That's sort of we like to use silly putty as an example of what the upper of the mantle is like. And then at the very, very outermost part, we have this eggshell. It's actually thinner than an eggshell surrounding the planet. That is the crust. That is the sort of plate in plate tectonics. And those plates move around. Here you see one sinking, and then in other places you have upwelling, forming new plates, or otherwise just coming up and forming volcanoes. And so we seismologists pull the Superman and use our X-ray, or in this case, seismovision, to see what these structures are. And in fact, it is seismology that tells us at what depth we have the inner core and the outer core. And in places like Mars, where we now also have a seismometer, we're hoping that seismology will tell us where the core is. So that's a real power that we have. And it works because anytime there's an earthquake on Earth, it sends seismic waves throughout the entire planet. So if there's an earthquake bigger than, let's say, a magnitude 6 that you hear about on the news, I can record it in my backyard. It doesn't matter where in the planet it is. And when those waves travel through the Earth, they bounce off and get deformed by all of the structures that they encounter on their path. And we can use that information once they arrive at our seismometers, wherever that is, to discern what those structures were, if we have enough data. And so this is in some ways akin to an X-ray. So here's an X-ray, and you can see the black areas are where the X-rays were able to make it through this person's torso and expose the film behind it, so it's black. And the white areas are the places where the X-rays reflected off something like bone, and therefore the film remained unexposed and white. Now, of course, the problem is if you have a structure right behind, let's say, this vertebra, you're not going to see it because the X-rays didn't get there. And so this is sort of a schematic diagram of that. Here's a woman holding a pineapple in front of her torso and a banana out to the side. And you imagine these light bulbs are your X-rays or your seismic waves. And if you just look at this light bulb in this shadow, you see a banana and you see that the arm is outstretched, but you don't know she has pineapple. And with this light here, you don't even know that her arm is outstretched, much less that it's holding a banana, but you can see the pineapple. And so seismology, like medical imaging, has figured out that the way to deal with this is to look at things from many different directions. So in medical imaging, that would be a CAT scan. So here you have an energy source that's generating X-rays and a receiver, some sort of an X-ray detector on the other side. And it spins around, it makes loud clunking noises that you probably hate, and takes images from all sides. And what that gives you then ultimately are sliced images through a 3D volume, right? So you can see all of the structures inside. So let's say we wanted to image some part of the interior of the Earth. Some people do the whole planet, or some people decide they want high resolution studies of particular areas. So as Eric mentioned, I'm interested in places where one plate is sinking down underneath another. Those were called subduction zones. And in these places, if we want to study those, we need more detail than you would get if you were just imaging the whole planet. So one example of a place where we have that happening is under South America. Here we have the Nazca Plate under the Pacific that's sinking underneath the continent, causing the Andes Mountains and the volcanoes that are part of them. Subduction zones are also what's responsible for forming continents. It's something that I think a lot of people don't think about. Why do we have continents? Why is the entire planet not underwater, right? That is essential to the type of life that we have on Earth. And it turns out it's also probably plays a big role in the type of atmosphere that we have because of the erosion and carbon cycling that happens when you have rocks above the water surface. So this evolution of the continent, and then the fact that many elements that we need, many of the things that we use, everything from ores to materials that we use in batteries, are concentrated in the continental crust precisely because of these subduction zone processes. So this is obviously a target both for seismologists and of earth sciences of all flavors to study what's happening here. And so here's an example of a study that I had recently. It was actually 2 projects that were out at the same time. This is Peru. So here's the capital Lima, there's Cusco, Machu Picchu would be somewhere down here, Juliaca, Lake Titicaca, and then this is Bolivia, La Paz, and then this is northernmost Chile. And the way to think about this is sort of, you take that CAT scan image from before and you put it upside down. So now the receivers are on the top, and these receivers are our seismometers. You can see that we put them out across the surface. And we initially, when you're coming up with a project, you put them on the map in a geometry that will best capture the structures that you're trying to image. So where exactly you put them, what geometry you use, is theoretically the best one to image the structure you're looking for. And so in this case, the downgoing Nazca plate was thought to have this very funky slab geometry where it kind of goes down, and then there's this weird bench, but only in one part and not the other. And we wanted to know what the details of this looked like. So you have this theoretical idea of where you would like the stations, but now you actually have to go and get them there. And that's, of course, always challenging because as it turns out, the places that are geologically interesting to go to are often places that are not the easiest to get to, right? These are places that don't have electricity, they don't have running water, they don't have any cables running to them at all. And so if you want to study them, you have to go there and put in some equipment. And so that's what I'll be talking to you about today. So this is every single one of those dots that you saw on the map. There are 90 dots on the map. Every one of those dots looks a little bit like this in theory. So you have a seismometer. So this is the actual instrument that measures how the ground moves, and it measures it in 3 directions: up, down, north, south, and east, west. And at least for most of the equipment that we have available to us, this is a very delicate, somewhat clunky, big, heavy, not waterproof piece of equipment. So we build a vault. We bury this underground, both so that it couples better with the basement rock, also that it's thermally insulated because temperature swings will cause noise in the data, and also that it's just protected. So we have a seismometer, we have a vault that's insulated, we run the cable out, we usually have to protect that cable. Then we have a box at the surface that holds this thing here called the DAS, that's the data acquisition system, or the computer that basically runs the whole thing. And then a battery and solar panels and a power regulator, an electrical system to help keep it running, even if there's no continuous power to be had where you're located. Most of the equipment that we have to use is provided by the Incorporated Research Institutions of Seismology, or IRIS. They're programmed for array seismic studies of the continental lithosphere, or portable. They changed that later. The idea was to democratize seismology, to have an instrument pool that all universities have access to that provides seismometers and ancillary equipment to be able to do this kind of work. And so here are 2 of the types of seismometers that they have. This is an STS-2, and this is a Graup 3T. And And then you have a box. This is this little black guy down here is a digitizer. This green thing is a power box, so that distributes the power from the solar panel to the battery to the computer. And then here's a battery, and the batteries that we use, they're like boat batteries. They're batteries that are designed to be fully discharged and then fully recharged if you need to. And then you hook this all up either with fire hose or PVC, and at least in theory, it ends up looking something like that. In reality, though, what we get from the equipment center is the instrumentation, not the boxes. So this particular type of box here is known as an action packer. And so if you hear me say that, that's what I'm talking about. They're lovely products that are very rugged, that we use a lot for this type of work. So Rubbermaid, if you're listening and you want to sponsor me, let me know. But in many countries, you can't get those. So you have to buy whatever you can get. And my favorite story of all time was from my colleague, Susan Beck at the University of Arizona. They ended up, the only thing that they could find were these plastic doll houses. There are these pink boxes, plastic boxes, that where the roof of the dollhouse would kind of swing open, and then they could put the equipment inside of that. And so they work quite well, my understanding. But so there is a little bit of MacGyvering that happens when you get in country and you find out what you can get there and what you can't. So once you have all of your equipment, you've shipped your equipment, you got it through customs, you've got your stuff from the store, you have your cement, you have your batteries. Now you need to get there. And the distances are vast. And whether the road is flat or mountainous, it is a long, long way to go. So you spend a lot of time driving. Sometimes you also spend a lot of time stopped. Things happen. You can see this was our van. We are the second in line here. This roadblock set up about 5 minutes before we got there, and they took it down 4 hours later. So we spent half a day at the roadblock. This is a head-on collision between a gasoline tanker and a double-decker bus at the very crest of the Andes that shut down the entire road for a day. So we had to go all the way back down off the mountain, and come back the next day to continue on. Sometimes the road just ends. So this was where we tried to get as far east as we could with our deployment in Peru. But ultimately, at some point, if you want to go further into the Amazon basin, you go by boat, which was something we were not prepared to do for this project. And so that is literally the end of the road. And then there's all kinds of wildlife and other sort of things that can share the road with you, and you just have to account for that. And then there are the things that can go wrong. I have changed countless flat tires in my career. Road maps, especially in very remote areas, tend to be more suggestions than true guidelines as to where the roads are. So we often stop and ask directions. What counts as a road on a road map is also a matter of taste, perhaps. And if you're wondering why we took a minivan down a road like this, it was because we could only find one pickup truck to rent at that time. And so those roads are very long. There are a lot of distances. And so we either have to go back and forth 4 times, or we had to go back and forth twice to get all the barrels and the concrete down there. So here you can see we're just absolutely loaded to the brim with equipment. So once you're there, then you have to find somewhere to put the station. And the trick there is that solar panels are wildly popular. It doesn't matter where in the world you go, they grow legs and wander off very quickly. So what we like to do is find people who are willing to keep an eye on the equipment for us for a couple of years. And so often that means finding out, sometimes it's very obvious people don't want to talk to you. Sometimes it's just a language barrier. In this case, this woman she spoke only Quechua, but her grandson spoke Spanish and Quechua, so he was able to translate for us, which was very helpful. If you're trying to install on private property, there can be endless red tape, and this is sort of one of my favorite combinations of signs. And then even if you do find people who are very excited to help, often in these areas, people have felt earthquakes. They know that this is an issue. They know that it's important to do this science, but it's often not just the landowner, but an entire community that's interested in the project. And the whole community wants to be informed on what it is that you're doing there, why you're coming into their community and installing this equipment. And so this was the elected head of this community, and I was sort of sketching out a seismic station for him to explain what we were doing. And sometimes you just don't find a spot. Sometimes a dot just isn't going to materialize. And then what you kind of have to do on the fly is redo all of that preliminary planning that you did on where the seismic waves are coming from, and how do you have to readjust all the other dots to make up for the fact that you're going to have that one gap. And so you're pulling out your laptop on the fly and rerunning some codes. So once you have your sites, then you have to dig a hole because you're burying a 55-gallon drum. So these are about 3.5, 4 feet high, and about yay wide, and you want them fully buried. And digging holes depends on what you're digging through, right? So if it's soft dirt, it's really easy, but often there are rocks in the way. This stuff that we were digging through was basically like a really compacted sandstone. And so my colleague here, Ryan Portner was digging through this, chipping away bit by bit, and it was my job to scoop out what he broke off, and I ended up with all this clay in my teeth. It was lovely. But generally, lots of work digging, and then sometimes, especially if you're at low elevations, you hit groundwater, and then you just have to dig a different hole at slightly higher elevation. Okay, then once you have your hole, you need to put concrete in it. We typically put concrete both underneath the barrel and in the barrel. That means schlepping a lot of sand and gravel in addition to the Portland cement that you're mixing with it. You need to know how to mix cement to get that right. You also critically need water, and sometimes you can bring that with you, and sometimes you just don't have enough room in the truck, and so you hope you can find it when you get there. So here's us in the middle of the Altiplano. The only water available at this site was from this 15-foot deep well, and we had a little bucket, and so we were scooping water to get enough of that together to make cement. Or you get it out of a canal, you pour the cement in, and then once it's in the barrel, you want to make sure it's good and level. So you're kind of reaching in to get that together. These are not popular photos. And then typically we put a fence around the whole structure. So you have these rolls of barbed wire. They're very heavy. So usually it takes 2 people to carry those around, and you string up the barbed wire fence. And then at that point, you're kind of at a standstill because now you need to wait for that cement to cure. And so at this point, you typically pack up and go back to where you started from, and you pick up the seismic instrumentation because you didn't have room for that in your truck before. So you drive back for a day, and then you drive back out for a day. Now you've got your equipment. Now it's time to install that. So here's us trying to install an STS-2. So these things weigh 25, 30 pounds. And so now you have a 55-gallon drum fully buried, and you're trying to lower this very delicate, somewhat slippery, 30-pound piece of instrumentation to the bottom of the barrel without dropping it. It's a great core workout. You have to orient it. So we want our north component pointing north, and we want our east component pointing east. This particular type of sensor, for some reason, has the orienting rod pointing east. You have to remember that. We've gotten that wrong before. And then you have to level it. Now the leveling bubble for this particular sensor is, it's right there, if you can see my pointer. So it's actually inset into the side, like a little cave into the side of the sensor. Now you can see how dark it is in these barrels, which means you have a flashlight in your teeth and a mirror propped up against the side of it. And then you have to twist these little feet, and you have to twist the top part separate from the bottom part because it's a locking mechanism to change the elevation to get that thing perfectly level and locked down. It takes some practice. So here's a picture of me in grad school. This is probably one of my first field photos ever, working on leveling it. And here's me doing the same thing 20 years later. Oh, one more word on the orienting. This is a Brunton compass. This is the standard geologist compass. They're, of course, based on magnetics. And you would be surprised how much metal is buried in the ground pretty much anywhere you go. And so if you put that Brunton down at the bottom of the barrel, you will get a very different reading than if you hold it up above. Also, you do sort of an airport routine where you're taking off your belt, you're taking off your watch, you're taking off any jewelry you may have, you take your wallet out, anything that's going to screw up the measurement, because you want to get that as accurately oriented as possible. So that's always fun. Once that's installed, then you've got to hook it all up. So you're running cables from the solar panel and from the seismometer into in this case, this action packer, and connecting everything together, making sure that voltage is going from point A to point B so that you have what you need and you are reasonably certain that this will stay fully charged and operational for the duration of the project. And then you can go ahead and do some testing. So we do this two ways. One is to do a stomp test, which is exactly what it sounds like. You tell someone to stomp their feet and you can see it immediately in the seismogram on your little handheld. The other thing, which takes a little more patience but is worth it, is to look for what's called microseism. So this is actually from the station I currently have deployed in my backyard. And you see this sort of, in this case, it's about a 4-second wave. Usually it's between 4 and 7 seconds. And those are waves crashing against the coast. We can record those pretty much anywhere in the world. And so if your station is quiet enough and level enough to record a microseism on both the vertical and more trickly on the horizontals, you know you're in good shape. And so to get that, typically you just have to kind of, everybody has to sit really still for 5 or 10 minutes. And then finally, you pack it up, you try to make sure everything's watertight and sealed, and you take a victory photo and you head out the door. And it just sits there and collects data on flashcards or on different types of memory storage devices for 6 months. And then every 6 months, you go back and you check on your data, you collect the data, and you make sure the station is still running. And usually it is, but sometimes it isn't. So this is the what could go wrong part of the talk. So this is my favorite photo here. So this circle here is that digitizer, and this, you have to unscrew this cap to get at the memory cards. And I don't know if you can see my buddy here, but she's got that hourglass right on her belly, and she's conveniently hanging upside down on the spiders in the web directly above the digitizer. Sometimes you walk up to a station and you see this, and the solar panel is just gone. And then the question is only when was it stolen and how much data did you lose? More extreme, this has thankfully only happened to me once. This was what was left of an action packer after I think some kids must have filled it with gasoline and set it on fire. That's what a battery, that's a car battery after it's been nuked. There was, fortunately, actually most of the sensitive equipment was not in the box at the time. We had temporarily pulled it for a short while because we were having trouble with the equipment, and we came back to find this, and we're very grateful that we had demobilized part of that station. This is a barrel with the seismometer at the bottom, and that is about 1.5 feet of condensation water that collected in that barrel over the course of a couple of years. The seismometer, bless it, actually continued to run, so we didn't notice that the water was accumulating until the end of the project. But normally, most sensors won't live through that kind of abuse. And what definitely won't live through that kind of abuse is if you soak electronics in a box with a battery. Once the electrodes on the battery get covered with water, you now have a charged soup. And this plug here used to look like this one. So that entire metal end to the plug just got dissolved off. So that's not great. So these are the things that you hope doesn't happen. We spend a lot of time thinking about how to keep water out of our stations, how to keep them charged, how to keep them running for as long as possible if the solar panel walks off. These are the types of things that we spend a lot of time worrying about. And then after 2 years, so you go back every 6 months for 2 years, and then it's time to go and you do everything in reverse. You dig the barrel back out of the ground, you pull your fence out, you pull out your solar panel and all of the cables. And then especially if you're shipping it internationally, you have to scrub it down, because if there are bugs in there after 2 years of being in the middle of nowhere, and you ship those back to the US, Customs and Immigration gets really, really angry. So we have to be very careful. And so we spend usually a full day with all the hands on deck scrubbing equipment. And then you go home and analyze the data. And so is it all worth it? I mean, it's a ton of work, right? So that is for one station. You can imagine here, we did it for 90. But I would say absolutely, because if you recall, this was sort of the geometry of the slab that we thought we had in the area. And after we used the data that we collected, this is what we found. And in the details, the differences are profound. We found a tear in the downgoing plate. It's just falling apart. And that means that we will probably eventually end up with volcanism in this part of the Andes where we haven't had any in a very long time, in the next million years or so. I don't want to get anybody worried. The geometry of this, the way there's sort of like a finger-like shoaling here, tells us how this geometry is formed and why. This extreme stretching of the plate here tells us something about the strength of the plate. It also affects the crystal structure, so it actually forms a fabric within that plate that we can image seismically. And the whole thing, this whole weird geometry, affects how the entire mantle interacts with this downgoing slab, which in turn has big implications for how it interacts with the plate above it, and how these mountains are formed and how the volcanoes react. So what's on the horizon? Well, we're looking at new technologies. And so I spend a lot of time talking to equipment manufacturers who make these seismometers and make the digitizers to help work towards making them more field robust. So the newest seismometers, you can just stick straight in the dirt. Now that is just revolutionary, right? No more barrels, no more concrete, none of that. You just put them right in the dirt and level them and orient them, pack them in with dirt, and you're good to go. They also take a lot less power. So your solar panels are smaller. And if you lose a solar panel, they can run for longer off of a given battery. The other thing that we've done is we've taken advantage of this new technology and we've created sort of a box to go. So remember, we had, when we usually get to our project, we first have to start off by going to, Home Depot or whatever the equivalent is and looking for the best plastic box we can find. And then praying that it's waterproof. And instead, what we now have are Pelican cases that are 100% waterproof. You can run this station at the bottom of the swimming pool. We have bulkhead fittings that we plug the seismometer into the box rather than having to cut a hole in the box and pass the cable through. So that's no longer a point of weakness. And it includes the solar panel and the solar panel mount and everything in a single box. So this was the brainchild of Tyler Bartholomew, who's one of our engineers at the machine shop that we have here in DC. And here we have 2 trucks. This is one station's worth of equipment for a traditional station. This was what we had for that entire project in Peru for a single dot. And this is what a single dot is with the new quick deploy box that we've developed. So this is just night and day. If you think about the amount of miles that you're driving and the hazards that go with that, just being able to bring all of the stations with you in one go and not having to wait for concrete to cure, it's just a whole new ballgame. And so, for example, I actually installed one of these, as I mentioned, in my backyard. So you can just hand auger a hole to some arbitrary depth. You pretty much don't want it deeper than arm's length, otherwise it gets hard to level and orient your sensor, but that's good enough. This whole station took me alone about 2 hours to install. And again, it's been sitting out there in some of the heaviest rains that we've had in the area in decades, and it remains 100% waterproof and operating perfectly. So that's very exciting. Oh, and one other point. This is the station in my backyard here along the fence. It's very small, very low profile. And if you're imagining trying to permit, you're trying to convince someone to have one of these in their backyard, the difference between that and this giant barbed wire installation, this is a much easier sell. So that makes life easier. And here's some earthquakes that I recorded. I thought that'd just be fun. Some of you may know that we had an earthquake in North Carolina, a magnitude 5.1 in August. So this is the recording in DC in my backyard of that. This is an earthquake from the middle of the Atlantic near the equator, so quite a distance away. And even so, we were able to pick up different types of waves that come with those types of earthquakes absolutely beautifully. Right, so let's see, how are we doing on time? We're doing pretty well. So just finally wrapping up, upcoming project that I have, it's slightly on hold because of the global pandemic, is in northwesternmost South America in Colombia. And so what we have going on here is these dots here represent earthquakes in the downgoing oceanic plate. And you can see that there's a big jump here between those 2 plates. And we want to understand what's happening there. And so I am leading up a big multi-institutional multinational project called MUSICA, Modeling Uplift Seismology and Igneous Geochemistry in the Colombian Andes. My part of that is primarily the coordination and the seismology, and also the education and outreach component, together with Marlena Jones at Carnegie's Academy for Science Education. But there's also geochemistry, geology, geodynamics, all different ways to look at the same system. And from the point of deployments, which is what we're talking about today, that's 75 stations that will be spreading out across much of the middle of the country. And so hopefully we can get back to that next year, or at least not too much after that. And we very much look forward to it. If you want to keep track of how the project is doing, please check out our website at musica.carnegiescience.edu. Websites are always a work in progress, but it is also bilingual. And if you like, you can also sign up there for updates. And so with that, I will end my presentation and take any questions that you may have.
Thank you so much, Lara. That was a fascinating talk. I feel like you're sort of Indiana Jones of seismology. So many fun fieldwork stories and so much great science. It's a perfect combination. So we have a number of questions about the crust and how thick it is. You had compared it to an eggshell in your introduction to the layers of Earth. And also people want to know, how far down into the crust can we drill, and would it be useful to put seismic instruments down that deep if we could?
Those are great questions. So the crust itself varies from anywhere from about 4 to 5 miles thick in the ocean to about 50 to 60 miles thick under the thickest parts of the continent. It's worth noting that the plate in plate tectonics is thicker than that, because there's part of the mantle that sort of freezes on to the bottom of the crust and acts as sort of part of that whole plate system. But the crust itself is actually very, very thin if you consider compared to the rest of the size of the Earth. We can drill, I believe the deepest drill hole is maybe 3 kilometers or 2 kilometers down. It's very little. We cannot drill through the crust. We can't even get close. The reason for that is that the pressures and the temperatures get high very, very quickly, and it just gets hard to move anything further. In terms of putting a seismometer down the hole, it doesn't get us much closer, and it definitely doesn't give us sort of the nice CAT scan in all directions kind of imaging. But it does make for very quiet seismograms. So in some places there are boreholes that have seismometers in them, but we're talking a few hundred meters, right? So we're not talking about anything approaching a mile, right? This is just a little bit deeper than what we usually do, just to get, what that does is it reduces sort of ambient noise from society, from people, or noise at the surface.
So would that then kind of filter out those soccer games stomping?
Yes. Yeah, the borehole seismometers would be much less good for picking up soccer matches. That's absolutely right. Yeah. There will also be some people who have looked at how background seismic noise has been affected when the coronavirus shutdowns first happened globally. All of the seismometers got very quiet. So we had very beautiful seismograms there for a while. But with borehole seismometers, that's less of a deal, because they are generally always very quiet.
So we have a number of people asking if it would be possible, instead of having to go back to each station and pick up the data, if you could have the data transmit via satellite or in some other way to some kind of central location, and if that's a possibility, and if so, why is it not used?
Yes, it is a possibility. It is used sometimes, especially in the US. You have a lot of different options. So you can use cell phone technology if you have access to a cell phone tower. You can use satellite data. If you have access to the internet, you can use internet data. But in the really remote areas where I was showing you, satellite's pretty much going to be your only bet. And that is very expensive for the amount of data that we're collecting and the amount of data you would have to stream. it is prohibitively expensive to telemeter that data in remotely. So for permanent stations that are used like for nuclear monitoring or global earthquake monitoring, these are very large, permanent, expensive installations. They actually make sure that they have some sort of a permanent connection so that they can stream that data in reliably. But satellite connection right now, unfortunately, is still out of our reach, just financially.
Thank you. We had a lot of people ask about that, so.
Well, it's worth noting if people are interested. I mean, one of the things that we have looked at doing, and we've in some of our quick deploy boxes, we have this incorporated, is maybe we don't get the data, but what we can do is at least get the seismometer to tell us how it's doing. You know, are you alive? Are you up and running? What's your battery voltage? What's your temperature? Are the masses oriented correctly? Is everything look copacetic? Maybe you can even get a short snippet of data. But that takes power. So again, you want to make sure that your power system is robust. And it still costs, last time I checked, I want to say it was something like $10 a month per station. And so that just very quickly for a 2-year deployment for, let's say, 100 stations starts to add up really fast.
So we have several questions about how you choose a site to deploy seismometers. Both of the big studies you talked about were in South America. Is South America a particularly interesting region, or is there just good opportunity for doing this there?
Right, so my research interests are largely, but not exclusively, for subduction zones, so places where you have one plate that comes in and dives down under the other. And South America, the entire western margin of South America, is a subduction zone. Now, some of the photos that I showed are also from Eastern Oregon, or actually much of Oregon. And of course, the Cascades and the volcanoes that we have there are also because of the subduction zone. And so we were studying some of that system out there as well. That was a larger Carnegie project in what was called the high lava plains. So it really depends on what the science question is that you're studying. A counterexample would be I had a big project in the southeastern United States, in Georgia, northern Florida, extending all the way up into North Carolina and even Tennessee a little bit. And for that project, we were studying an ancient suture. So at one point, all of the continents had come together into a supercontinent called Pangaea. Some people may have heard of that. And at that point, when that broke apart, Florida, which wasn't previously sort of part of what we think of as North America, stayed behind and everything else moved away from it. And so that suture where Florida kind of got sutured on is along what's called the Brunswick magnetic anomaly. And so we had 2 lines of seismometers going right through there to try and image what that suture might look like. So what does it look like when you glue one piece of continent onto the other, and why didn't it break apart at the same place?
So what you're saying is even geologically, Florida is the weird state.
But Florida loves us so much, it didn't want to leave.
Well, that's a very nice way to think about it. So several people have asked, how many installations do you have, and how many of them are these quick deploy boxes, and how many of them are the more traditional style, and what will it take to transition entirely to the easier quick boxes?
So right now we have 20 quick deploy boxes that do the type of science that I do. We have another dozen that are used specifically for volcano science. My colleague Diana Roman is a volcanologist, and so she uses those on volcanoes. We're hoping to get, if we typically try to get a couple more every year, they're not inexpensive. So that's sort of the bottleneck there. Both the Instrument Center and Carnegie are sort of trying to find ways to increase the numbers. The potential, of course, is that if you think about how much work it would be to do the 75 stations in Colombia with the traditional gear, for the same amount of work and for the same amount of money and for the same amount of time, you could put in hundreds of these quick deploy boxes. And that just means if you think of each of them as like a pixel in a photo, you just get that much better resolution. So we're working on it.
Well, we'll have our fingers crossed for you. We want that great data, and we want your life to be easier. So we have a question. This is definitely a little out of your wheelhouse, perhaps maybe more in some of your colleagues at Earth and Planets Laboratory, but you had mentioned the Mars seismometer, and what have we learned from that so far, and what can we anticipate learning from it?
Yeah, so I will say I have not worked on these data myself, but I keep an eye on it because it's an exciting project. It's kind of amazing. I think about how hard it is to get one of these stations installed on Earth, and I'm just blown away that they were able to do that remotely on Mars. They are getting good data. They have had some earthquakes, Mars quakes, or I should say Mars quakes. Mars quakes look different than earthquakes, and most of the ones that they've had so far have been quite close to where they put the seismometer. So I think I may be a little behind the times. I think they're still looking to see if they can get that core structure from those Mars quakes. The other place that they may be able to get that data is if they have a big impactor. Of course, Mars has less of an atmosphere than we do, so they get hit more often, though these days it's still pretty infrequent. But they have gotten a lot of information about what the Martian crust looks like. I have to say the details of that are something that I am not up on, but it's exciting enough that they've been able to record actual Mars quakes on Mars, a planet where we usually think of being tectonically dead. But apparently you don't need plate tectonics the way we think of plate tectonics to get an earthquake.
Very exciting, and definitely so much more to learn as we get to explore Mars more and more, as some of your colleagues are involved with doing. So we have time for one last question. We aren't able to get to all of them, but if anybody did not have their question answered and would like to email it to events@carnegiescience.edu, we'll make sure to pass that along to Lara, and she will answer it for you. She's generously agreed to spend some more time doing that because we have so many questions. So we have about 4 people asked whether, and if so, how shifts in the Earth's magnetic field affect your work, if at all?
Thankfully, no. So it's true, the Earth's magnetic field is constantly moving. The biggest place where that comes up is that when we go to do a deployment, we check the correction that we make to magnetic north. So our compasses are magnetic, and you need to correct that for true north. In other words, the rotation axis of the Earth, which is not actually the magnetic North Pole, and where the magnetic North Pole is moved. So you can actually look up, you can do this on the internet, you can look up what the correction is today at a particular location on Earth. How would you need to correct your compass to get to true north? And then we assign that. And now if your project is particularly large, you may actually want to have different corrections for different parts of the project, depending on where you're located. But other than that, in terms of actually recording the data, the seismology itself is not affected as long as you know which way is north.
Okay. Thank you so much, Lara. That was a great talk. It really was fantastic, giving us not only insight into the inner workings of the Earth, but also insight into what it takes to be a geophysicist with a passion for studying what's inside the Earth. I think the key word was schlepping. I heard that. So, but really appreciate that. I also want to thank our audience for the great questions. This is just a great number of questions. Sorry we couldn't answer all of them, or Lara couldn't, but we'll try to get to those later. But thank you for your dedication to Carnegie and for your attention to this great talk. Lastly, I'd like to invite you back on December 14th at 10:30 a.m. this time, when John Mulcahy, the director of our observatories in Pasadena in Chile, is going to talk about the upcoming solar eclipse. There'll be another total solar eclipse that will occur on that day over Patagonia. And after he'll talk to us a bit about the meaning of the solar eclipse, but afterward, you can stay with us for the NASA live stream of the totality of this most amazing celestial event, which occurs at 11 a.m. Eastern time. So I hope you'll join us for that. And with that, thank you all so much. Thank you again, Lara.